Hi students, in this class we will discuss about the concept of region of convergence of Laplace transform. Concept of region of convergence of Laplace transform. Simply ROC, region of convergence. Region of convergence is nothing but ROC. Okay, I will explain you about the region of convergence, and along with that I will give the properties of ROC, and I will give the conditions for the existence of Laplace transform. So in this class we will see what is region of convergence and what are the conditions for the existence of Laplace transform, and then I will explain you some of the properties of this region of convergence of Laplace transform. So this is what I am going to explain you in this class. First I will start with region of convergence. What is a region of convergence? ROC. Simply, ROC is nothing but the range of values of real part of S. Range of values of real part of S means S is nothing but the combination of sigma plus j omega, that is real and imaginary. So here I have to consider range of values of real part of S. Real part of S is nothing but sigma. Real part of S is sigma, because we all know S is nothing but the sigma plus j omega. In that the real part is sigma and the imaginary part is this one, omega. Omega is the imaginary part and the real part is sigma. So the range of values of real part of S, that is sigma. So I can say this, the range of sigma for which the Laplace transform converges. The range of sigma for which the Laplace transform converges is known as region of convergence. Simply ROC. So here it is nothing but range of values of sigma, that is range of a variation of sigma, or range of values of sigma, where sigma is nothing but the real part of S. So it is a range of values from this value to this value. So if the sigma value, that is the range of values of a real part of S, so the range of values of sigma for which the Laplace transform converges. Here the Laplace transform does not converge for all values of S in S plane. So if there is an S plane, in that the Laplace transform does not converge for all values. It will converge for only some values of real part of S. For that only it will converge. So for those values for which the Laplace transform converges is nothing but the region of convergence. Here that convergence is based on the values of sigma, nothing but real part of S. So hence I concluded the range of values of real part of S, that is sigma, for which the Laplace transform converges is known as a region of convergence. Simply it is nothing but ROC. Okay, ROC. Okay, that is what a region of convergence is. And for the existence of Laplace transform, it has to satisfy some conditions. So the conditions for the existence of Laplace transform is, first one, x of t is either continuous or x of t is piecewise continuous in the given closed interval. Here the given signal x of t is piecewise continuous in the given closed interval. And the second condition is x of t into e power minus sigma t. X of t into e power minus sigma t must be absolutely integrable. Simply that is nothing but integral of mod of this value. Integral of mod of this value dt is less than infinity. That is, it will be a finite value. So the integration of this value must give a finite value. Okay. If these are satisfied, then we can say that Laplace transform may be existed. Okay, so the conditions for the existence of Laplace transform is, the first one is x of t is piecewise continuous in the given interval, and the second one is x of t into e power minus sigma t must be absolutely integrable. Absolutely integrable means it must have a finite value, that is integral of x of t e power minus sigma t dt must should have a finite value. Okay, so these are the two conditions, these are the two statements for the existence of Laplace transform, that it has to satisfy these two conditions for the existence of Laplace transform. Okay, first I explained you what the region of convergence is, and then I explained you what are the conditions for existence of the Laplace transform. Now we will focus on the concept of ROC, that is region of convergence. Okay, so in that everything will be explained by the properties of region of convergence of Laplace transform. So you can get the clear idea about the region of convergence with the help of properties of ROC. Okay, properties of ROC of Laplace transform. The first property is the region of convergence contains strip lines parallel to j omega axis is in S-plane. The ROC contains strip lines parallel to j omega axis in S-plane. So let us consider this as S-plane. So S-plane consists of the sigma on x-axis and j omega on y-axis. J omega on y-axis. So here ROC, the region of convergence, contains strip lines parallel to j omega axis. This is j omega axis. For this, it will be parallel. Okay. So the region either this side or this side. So or in between two values of h sigma. Okay. Anyway, it will contain strip line. Okay, like this strip line is parallel to j omega. The strip line is parallel to j omega axis in S-plane, like this. So we consist of strip of lines. Okay, we consist of strips parallel to j omega axis. That strips will give the region of convergence. Simply the first point, region of convergence contain strip lines parallel to j omega axis in S-plane. And next point, ROC does not contain any pole. ROC does not contain any pole. Generally, an equation consists of numerator and denominator. So we all know that. So here, an equation consists of numerator and denominator. Here, the numerators will give zeros and the denominators, if we equate the denominator to 0, then we get the poles. We get poles, concept poles. Okay, so the ROC does not contain any pole. That is the region of convergence does not contain any pole, because at that pole the value of the Laplace transform will be infinite. But we have to get a finite value. For that, we don't get, that is the ROC does not contain any pole. So pole is nothing but, in a given equation there is numerator and denominator. If we equate the denominator to 0, then I get the pole. So if there is a value like s minus a in the denominator, if in the denominator I have term like 1 by s minus a, so equate this to 0, so that s equal to a. So a is a pole. Now the region of convergence is either greater than this one or less than this one, based on the type of signal. Either it is a right sided signal or left side signal. That is based on the signal that is given data. So this value, that is the region of convergence, will change along with this value. So here that a is nothing but the pole, because if we equate this one, so then s equal to a, so that is the pole. So the region of convergence does not contain that value. Okay, does not contain this value, a value. Okay, either it may be greater than a or less than a. Region of convergence is either greater than a, less than a. So how they will be, see in the next point. So the third one is, if x of t is absolutely integrable and is of finite duration. See, if x of t is absolutely integrable and is of finite duration, then ROC is entire S-plane. So here the given signal x of t is absolutely integrable. So the integration of that x of t will give a finite value. Okay, and the signal is of a finite duration, and the given signal is of finite duration. Then ROC, the region of convergence, is entire S-plane. It is the entire S-plane. Entire S-plane is the region of convergence. Okay, so if x of t is absolutely integrable and is of finite duration, then ROC is entire S-plane. This is the first one. And now we will get the region of convergence for different types of signals. Okay, with respect to this pole. See, we will see this. If x of t is a right-sided sequence, so it is right-sided. Okay, for a right-sided sequence, the ROC, that is nothing but real part of S. For the ROC is real part of S is greater than sigma naught. So sigma naught is on value on sigma axis. Consider that as a pole. Okay, then the real part of S should be greater than that one. So if this is like this, S minus A, so S equal to A. In this case, if the signal is a right-sided sequence, then the ROC, the region of convergence, is real part of S should be greater than this value, that is, for a right-sided sequence, the ROC is the right side of the atmost pole, okay, the final pole. From, if there are 3 or 4 poles, at most pole we have to go for the right side. That means in that ROC we don't consider, we don't have any poles. So if there are two equations, S minus A and S minus B, A and B, 2 poles, so we have to take the rightmost pole. So there is a pole at this point, there's a pole at this point, so I have to consider the rightmost pole. From that I have to go for the ROC. Okay, so for this, if there is a plane like this, sigma and j omega, here is a pole and here is a pole, and the given signal is a right-sided sequence, then we have to consider the rightmost pole. So this one, from this I will get the sequence, will get the region of convergence, will get the ROC. So ROC is right side, it is right side to the rightmost pole, and in this ROC we don't contain any poles. If you take ROC from this point, then this pole will be included in this ROC, so we have to take the rightmost pole. Or simply we can write like this, that a real part of S should be greater than that sigma naught. So is the value, that is the value on that sigma axis, okay, greater than that one. Next, if x of t is a left-sided sequence, then ROC is real part of S less than sigma naught. That is, sigma is less than sigma naught. The sigma value is less than sigma naught. Okay, so the region of convergence is to the left side, simply sigma j omega. So here also, if you have 2 or 3 poles, okay, then I have to consider the left side, okay, leftmost pole, and from that the region of convergence. This whole thing is region of convergence, that extends up to infinity, starts from that pole point and extends up to infinity. Okay, this is the ROC. Or the poles are like this. If it is a left-sided signal, then I have to consider this one and I have to go for this one, like this. So this is the region of convergence for left-sided sequence. So if x of t is a left-sided sequence, then ROC will be equal to real part of S should be less than sigma naught. Okay, and the sixth one, if x of t is a two-sided sequence, that is it is a combination of right-sided and left-sided. The best example for right-sided sequence is causal, or simply you can take u of t will give only the values greater than 0, that is right-sided, and u of minus t, that is left-sided, or simply anti-causal. Okay, now if x of t is a two-sided sequence, it consists of both u of t and u of minus t, okay, both the values, then the ROC is the combination of two regions. Okay, sigma j omega. Okay, so we have 2 poles, this is one pole and this is another pole. Okay, so here from this one right-sided, it will be like this, and from this on the left-sided, then that will be, it will extend up to infinity, Now we get the combination of the two regions. So this combination of the two regions, this is nothing but the ROC for a two-sided sequence. The combination of two regions is the ROC, region of convergence. The ROC of the sum of 2 or more signals is equal to the intersection of ROCs of those signals. Simply, if I want to find out the region of convergence of sum of 2 or more signals, I have taken 2 or 3 signals or 4 signals, and that ROC of the sum of the two or more signals is equal to the intersection of ROCs of those regions. Simply, see here, the first signal is having a pole here, and its region of convergence is like this. Okay, and next one is a pole here, and the region of convergence is with this. Okay, and the third one is here, and the region of convergence is to this side. Okay, see here the combination of these three. So from first point, this all part, second from this all parts, third it is from this, but here we have only two signals, that is with respect to this and with respect to this, but this pole is from this point to this. So the intersection of these three poles is this one. So this is the area. So I can take this area, so this intersection of these three is ROC. That is, the ROC of sum of two or more signals is equal to the intersection of the ROCs of those signals. Clear? So, or simply, if x of t is a two-sided sequence, then ROC is the combination of two regions. So here is one pole, because it is two-sided. One will come to the right side and other will come to the left side. Then I go for the combination of the two regions as the ROC. The combination of the two regions as the ROC, region of convergence. Okay, so these are the properties of ROC of a Laplace transform. So based on the properties, we can get the ROCs of different signals after finding the Laplace transform. Okay, we can get the region of convergence of different signal after finding the Laplace transform of that signal. Okay, so in this class I had given you the definition for region of convergence. What are the region of convergence is? So simply, the region of convergence is nothing but the range of values of real part of S, or simply the range of sigma for which the Laplace transform converges is known as region of convergence, because the Laplace transform does not converge for all the values. It will converge for some values of sigma. So for those values for which the Laplace transform converges is known as the region of convergence. And the conditions for the existence of Laplace transform is, first one, x of t is a piecewise continuous in the given closed interval. That is, x of t is continuous or x of t is piecewise continuous in the given closed intervals. And the second condition is x of t into e power minus sigma t must be absolutely integrable. That means the integral of this one will give a finite value. Okay, and next I explain you the properties of ROC. So simply ROC is nothing but the range of sigma for which the Laplace transform convergence is known as ROC, region of convergence. Now I will see the properties of ROC. The first property is the ROC contains strip lines parallel to the j omega x. Strip lines parallel to j omega axis. Next, ROC does not contain any pole. So ROC, that is region of convergence, does not contain any pole. Okay, next, x of t is absolutely integrable and it is of finite duration, then ROC is the entire plane. If the given signal is absolutely integrable and it is of the finite duration, then the region of convergence is complete S-plane. This S-plane is having sigma on x-axis and j omega on y-axis. Okay, now if x of t is a right-sided sequence, then ROC is real part of S greater than sigma naught, or simply if the x of t is a right-sided sequence, then the region of convergence is to the right side, rightmost pole. It starts from the rightmost pole and extends up to infinity, and inside that ROC no pole will exist. Okay, so it starts from the rightmost pole if there are two or three poles. If x of t is a left-sided sequence, then ROC is nothing but the real part of S less than some sigma naught value, that is some value on that sigma, that is a pole less than that pole. Or simply, if there are two or three poles, then it will be leftmost pole, and it is to the left side and it extends up to infinity because it does not contain any poles. The region of convergence does not contain any pole inside that one. And if x of t is a two-sided sequence, then ROC, if it is two-sided sequence, that is the region of convergence is right to the right side, and for another pole it is to the left side. Then the ROC is the combination of two regions. So the intersection of those two regions will give the ROC if it is a two-sided sequence. Or simply you can say that the ROC of the sum of two or more signals is equal to the intersection of the ROCs of those signals. If there are 3 or 4 signals and we have the different ROCs for each signal, then the combined signal will have an ROC of intersection of all those regions. So in this class I explained completely about the region of convergence, the concept of region of convergence along with its properties. Okay, this is today's class. With this, I am finishing today's class, and we will see the some more topics in the next class. Okay, thank you, one and all.